Good morning, friends. Last topic of this chapter, Davison and Gerber's experiment. Right? Here our aim is, already we discussed about the dual nature of matter. In some circumstances it acts as a particle, and in some circumstances the matter is act as a wave. Here we want to find out the wavelength of an electron corresponding to its wave nature. Right? For that purpose, the Davison and Gerber performed the experiment. The arrangement of this experiment is shown in the figure. In figure, here the electron gun. So that is connected with the low tension battery. As the current passing through the filament, so filament is heated, and due to the thermionic emission of electrons are emitted by the filament. This emitted electron passes through the cylindrical arrangement to make this electron as a beam. So that is known as the electron beam. For that purpose, what are the electrons are emitted by the filament are accelerate, that means its velocity is going to increase. Due to that purpose, here the cylinder is made positive compared to the filament by high tension battery. Here the high tension battery, this arrow shows there is the variable battery. We can make the change of applied voltage to the cylinder. So this arrow represents the variable battery. So by changing the position of this pointer on a variable resistor, so we can increase or decrease the potential applied to this cylindrical arrangement. So here the cylinder is kept positive with respect to the filament. Therefore, all the electrons emitted by the filament are attacked by the electron beam or the cylinder. And as a result, these electrons are passing through this very small wall of the cylinder. It forms the electron beam, and its velocity is also the definite velocity. With definite velocity, this electron beam is incident on a crystal. Here, the Davison and Gerber consider the crystal as a nickel. So, this electron beam is incident on nickel, and due to the atoms of this crystal, the electrons are scattered in all directions. That means, after the incident, they are scattered in all directions. To detect the scattered electron in particular direction, here the movable collector is arranged. So this collector can move by 360 degrees in all directions, and it can measure how many electrons are scattered in particular direction. So here the angle can be measured with the direction of incident electron beam to the scattered electron beam. So this angle theta gives the particular direction, and how many numbers of the electrons are scattered in particular direction can be measured by this collector is connected with a sensitive galvanometer. So this sensitive galvanometer shows the current flowing through the circuit. That means what are the electrons are collected by the collector passing to the galvanometer, that shows the deflection, and the deflection of the galvanometer shows the amount of the electron deflected or the scattered in particular direction. This entire arrangement is kept in evacuated chamber. So as a result, the atmospheric particles are not scattered or not detected by this cylinder. Okay. Now, after the arrangement, what is the description of this figure? Figure shows an arrangement of Davison and Gerber's experiment. It consists of an electron gun with tungsten filament. Here there is the electron gun. In electron gun, one filament of tungsten is given. As the current passing due to the low tension battery, so filament get heated. And this filament is coated with the barium oxide. The layer of the barium oxide is done on the filament and heated by a low tension power supply. So as the switch on of this low tension battery, current passing through the filament, and as a result, the filament get decayed, and due to thermionic emission, the electrons are emitted, which are accelerated by high tension battery. So what are the electrons are emitted by the filament? These all the electrons are attacked by the cylinder. This cylinder is connected with high tension battery. That means the high voltage is applied to this cylinder to desired velocity, and as a result, this emitted electron is converted into the beam, and its velocity we can fix. These electrons are made to pass through a cylinder with the 5 holes along its axis, producing an electron beam. So these electrons are made to pass through a cylinder with 5 holes. Here the small holes are given on a cylinder to form an electron beam. And this electron beam is incident or the fall on the nickel crystal. The electrons are scattered in all directions by atoms of the nickel crystal. So what are the electrons are incident in form of a beam? They are scattered in all directions. For simplicity, we consider only the single direction. These electrons are scattered in this. But actually that's not right. In all directions, the electrons are scattered. This direction, this. Okay. The intensity of the electron being scattered in given direction is measured by the electron detector or the collector. So how many numbers of the electron are scattered in particular direction can be measured with help of the collector. This collector can be moved on the circular scale. So there is not a fixed, there is the variable, there is the moving on a circular scale. The collector can move on a circular scale, and it is connected to a galvanometer, which measures or records the current. Because the current is flowing due to the numbers of the electron collected by the collector and this electron passing to the galvanometer. The deflection of the galvanometer is proportional to the intensity of the electron beam entering the collector. So, what is the deflection of this galvanometer? The deflection of galvanometer is directly proportional to the intensity of the electrons scattered in particular direction. Okay. The apparatus is enclosed in evacuated chamber. This entire arrangement is inside the evacuated chamber. Clear this? Okay. So there is the arrangement of Davison and Germer's experiment. That is the evacuated chamber. Here, so there is the arrangement of Davison and Germer's experiment. Just we discussed about the arrangement of Davison and Germer's experiment. Now, what is the method and result of this experiment? Now here, in Davison and Germer's experiment, the detector, that means the collector, can move on a circular scale, and we can aim the different position of the collector. To know that in particular direction, how many numbers the electron are scattered. Right? Okay. The angle between the incident beam and scattered beam is known as the angle of scattering, because frequently we are using the word scattered angle or the angle of scattering. Again, the definition of the angle of scattering is that the angle between incident beam and scattered beam is known as the angle of scattering. Already we mentioned in the arrangement of Davison and Germer's experiment. Right, okay. For different accelerating voltage, that means the voltage of the high tension battery and different scattering angle theta, the intensity of the scattering beam is measured in Davison and Germer's experiment. In this experiment, for different accelerating voltage V and different scattering angle theta, the intensity of scattered electron is measured. The Davison and Germer performed this experiment weighing the accelerating voltage from 44 to 68 volt. Again, the Davison and Germer performed the experiment weighing accelerating voltage from 44 to 68 volt. They found that means it was noted that the maximum intensity I, that means the maximum number of scattered electron in particular direction of the scattered electron for accelerating voltage 54 volt and the scattering angle theta is equal to 50. So during this experiment, they measure the intensity of the scattered electron in particular direction. That means that different angle with the different value of the voltage. Voltage is varying from 44 to 68 volt. They found that at 50-degree angle, scattered angle, and 54 volt, they obtained the maximum intensity of the scattered electron. So, if the stationary electron is accelerated by voltage V, so its kinetic energy K is equal to EV. We know that kinetic energy is equal to half mv square. Therefore, half mv square is equal to EV. Right? But we are interested to find out the wavelength of an electron. According to the de Broglie's wavelength, the equation of de Broglie's wavelength lambda is equal to h upon p. And due to that reason, we have to convert this equation of kinetic energy in terms of the momentum. So here the mv square is present. S will multiply and divided the left hand side by m. Therefore, EV is equal to m square v square upon m, and that is 2. That means EV is equal to m square v square upon 2m. We know that the momentum P is equal to mv. Therefore, EV is equal to P square upon 2m. Clear? And from this equation, P square is equal to 2m EV. Therefore, P is equal to under root of 2m EV. So, that is the equation of momentum of an electron scattered at 50-degree angle and 54 voltage. Clear this? So, that is the method of the Davison and Germer's experiment. They obtained the momentum of scattered electron. Okay. Now, the wavelength of matter, wave, that means the electron. De Broglie's wavelength lambda is equal to h upon p. Just we obtain the equation of the p momentum. P is equal to under root of 2m ev. Here we substitute this value. Therefore, lambda is equal to h upon under root of 2m ev. Here the h is the Planck's constant, m is the mass of an electron, and e is the charge of an electron. So, substituting the value of h, m, and e. H is 6.626 into 10 is to minus 34 joule into second. M, mass of an electron, 9.1 into 10 is to minus 31 kg. And E, charge of an electron, 1.6 into 10 is to minus 19 coulomb. S is substituted in this, so we obtain the wavelength lambda is equal to 1.227 upon under root of nanometer. Okay. Now, if we substitute the different value of accelerating voltage, we obtain the wavelength of the scattered electron in particular voltage in particular direction. Okay. So, theoretical value of wavelength of an electron is 0.165 nanometer. Theoretical value of wavelength of electron corresponding to its wave nature is 0.165 nanometer. While the Davison and Germer obtained the experimental value of wavelength at 54 volt is 0.167 nanometer. So here both values are very close to each other. Thus, in this experiment, there is the excellent agreement between the theoretical and experimental value of wavelength of an electron. Thus, the Davison and Germer also prove that the electron behaves as a wave. And corresponding to its wavelength is very close to the theoretical value 0.165 nanometer. At 54 volt, they obtain 0.167 nanometer. So Davison and Germer's aim to prove that the electron behaves as a wave or not. And if the electron behaves as a wave, so what should be the wavelength of this electron? So they obtain the wavelength of this electron. Now listen, this equation is important. Frequently the objective question in board exam, NEET and also good set, that is asked, lambda is equal to H upon under root of 2 MeV. The voltage is given at particular voltage. Generally the 54 is given. Generally 54 is given. H is substitute the 54. H is Planck's constant, M is the mass of an electron, and E is the charge of an electron. We obtain the wavelength is 0.167 nanometer. Clear this? Okay. So here the chapter 7 is theoretical is completed. Theory portion. And already we discussed the two numerical of illustration. Now we start from the third illustration. Earlier we discussed the first and second illustration. Now the third illustration about the photoelectric emission. In the wavelength of light in visible region is about 390 nanometer for violet color. For violet color, the wavelength is given the 390 nanometer. Now about 550 nanometer for yellow green color and about 760 nanometer for red color. What are the energy of the photons in electron volt at end of above visible spectrum? Here the value of the Planck's constant and 1 electron volt is equal to 1.6 into 10 raised to minus 19 joule is given. First we discuss or we calculate the energy of the photon in electron volt for given the color of visible spectrum. Right? Here the Planck's constant H is given, 1 electron volt is given, and we also require the value of C, speed of light or the speed of photons in vacuum 3 into 10 raised to 8 meter per second. First part is energy of photon, incident photon. We know that the E is equal to HF. E is equal to HF according to the characteristic of photon. Now we know that F is equal to C by lambda. Therefore, C upon lambda, this energy is in joule. But we require the energy in electron volt. Therefore, to convert the energy from joule to electron volt, we have to divide this energy by charge of an electron. Therefore, E is equal to Hc upon E lambda in electron volt. Now, first for whatever the color is given, violet. For violet, wavelength of violet light is given, lambda V is 390 nanometer. 390 nanometer. Now nanometer is equal to how much meter? 10 is to minus 9, and this 0 again, therefore 39 into 10 is to minus 8 meter. Therefore the energy of photon for violet light, energy of photon for violet light is EV is equal to Hc upon E lambda V. H is equal to 6.6 63 into 10 is to minus 34. C is 3 into 10 is to 8. Now, E is given 1.6 into 10 is to minus 90 into lambda B 39 into 10 is to minus 8. So as we calculate it, so answer is 3.19 electron volt. Calculate yourself. That is the energy of photon for violet light. Now second for yellow green light. Energy is E by Z. First, what is the wavelength of yellow green light? Lambda YG, yellow green, is given as 550 nanometer. Is equal to 55 to 10 is to minus 8 meter. And energy E by G for yellow green color is equal to HC upon E lambda Y G. So as we substitute the value of HC, E and lambda, 55 to 10 is to minus 8 meter, we obtain there is a 2.26 electron volt. And third for red color, wavelength is given lambda R, that is 760 nanometer, is equal to 76 into 10 is to minus 8 meter. And energy ER is equal to HC upon E lambda R. According to this equation, our standard equation is this, HC upon E lambda. Therefore, HC upon E lambda R. If we substitute the value of H Planck's constant, C is the velocity of light, and E is the charge of an electron, and lambda is the wavelength of red color. So we obtain the energy of photon for red color is 1.64 electron volt. Now this value of E by Z and also E are calculated by substituting the value yourself. I directly write down the answer for this value and this. Now in B part, here the work function for photosensitive material cesium is already given 2.14 electron volt. For potassium, that is given 2.30 electron volt, and for sodium 2.75 electron volt. Now we want to build a photoelectric emission device for given light of visible region, violet, yellow, green, and also the red light. For which color and for which material we can prepare the photoelectric emission. For that purpose, first, for violet light, first thing, what is the condition? The energy of the incident beam must be greater than the work function of a given metal, or equal to the work function of a given metal to produce the photoelectric emission. So first thing is condition for photoelectric emission. The energy of incident photon is equal or greater than work function of a given material or the metal. First, for violet light, energy EV is, what is the value of EV for violet light? 3.19 electron volt is more than the work function of cesium, potassium and sodium, is more than 50 of cesium, potassium and sodium. So that photoelectric emission is take place. Photoelectric emission can take place. It means we can build the photoelectric emission with any material, that means the metal, either the cesium, potassium or sodium, if we incident the violet light. So photoelectric emission is take place. Now for second, for yellow green light, energy of incident photon YZ is already we have 2.26 electron volt. 2.26 electron volt. Now 2.26 is greater than the only for cesium, while for potassium and sodium there is the less value. Therefore we can't prepare the photo emission device by using the sodium and potassium. Is more than 4. More than work function for cesium, but less than 4 potassium and sodium. So that with cesium, photoelectric emission take place. But for sodium and potassium, not take place. Because the work function for yellow-green, the energy of yellow-green light is more than the work function of cesium. That is the 2.26 is greater than the 2.14. While for potassium and sodium there is less value. Therefore, for metal with the potassium or sodium, the photoelectric emission does not take place, while for cesium there is take place. Now, third part for homework, for red light the work function is 1.64. That is less than the work function of cesium, potassium and sodium. Therefore, we can't prepare the photoelectric emission by using the cesium, potassium and sodium with red light. Right? So last portion, do yourself. Again, for red light, the energy of incident photon is, that is the 1.64 electron, is less than the work function of cesium, potassium and sodium. Therefore, the photoelectric emission does not take place. Clear? Because in the beginning for the photoelectric emission, the minimum energy required to emit the electron from the photosensitive material So that is known as the work function. Right? So that much minimum energy is required to emit the electron from the photosensitive material. If the energy incident is less than the work function, in that case the photoelectric emission does not take place. If the energy incident on the metallic surface is more than the work function of metal, in that case the photoelectric emission takes place. Clear this? Okay. So third part, write down yourself the same one. Okay.